Algebra 2 students. Mrs. Myers here. Unfortunately, we are not live together today. Hopefully all will go well and we'll be live together tomorrow on Friday. But for today, I am hoping that you're going to be able to understand what I'm trying to teach you in lesson 15 day 1 just by watching this video here. And then we'll finish and do some more practice with it in lesson 15 day 2 tomorrow when we have a live Google Meet. Okay, so this is posted already for you on Google Classroom. So if you have not yet printed it and you do have a printer and you can print it, why don't you go ahead and do that? If not, then try to get the main concepts of this down in your notes, okay, if you're just copying on loose leaf paper, okay? So we've been talking about graphs of polynomial functions already. We've talked about using different techniques and how we can use, a factored form to identify the zeros, and we can use the zeros to get the x-intercepts, and then we can use those zeros to divide up the graphs into different intervals and pick test values and see if the function evaluates to be positive or negative, and then that would mean that the graph is either above or below the x-axis within that interval, and we've made the graph of the polynomial function, right? So anyway, we're still going to be doing graphs of polynomial functions, but now we're going to be taking a look at a little bit more information with respect to some techniques that can be used to make the graph of this, okay? And they're going to tie together nicely with what we've done already before, and they're just going to kind of give you another approach. So what's important to learn here, okay, is there's a way to determine what the ending behaviors are going to be for a graph. Okay, that means from the x-intercept that's furthest to the right, as the graph continues to go with x's approaching positive infinity, what are the y's going to do? That's an ending behavior. And also, when you look at the x-intercept that's furthest to the left, and you're going to go continue to the left with the graph, like meaning as x's approach negative infinity, what are those y's going to do? So there's really only two things that the y's will do. Remember, I've been telling you the graphs are just going to forever go up, or they would just forever go down. So which is it going to be, okay? So there's really, it's based on your degree of your polynomial function, and it's based on the leading coefficient, okay? So with your even degree polynomial functions, okay, the degree means your highest exponent. Okay, so again over here, this means your highest exponent. Okay, so if your degree is even, okay, which obviously means if the highest exponent you see is a 2 or a 4 or a 6, okay, then depending on what your leading coefficient is, either positive or negative, your ending behaviors will either both be up or both be down. Okay, so we got the sentence back up here. It says even degree polynomials demonstrate the same ending behavior as x approaches positive infinity as it does with x approaching negative infinity. That's really, really important to know. So your ending behaviors are either going to be that they each go up, up, up forever towards positive infinity, and that's if you have a positive leading coefficient. Okay, that just means if the number in front of the term that has the highest exponent is a positive number, that meaning that's a positive leading coefficient, then you know that you're automatically going to have ending behaviors that go up. But if you have a negative leading coefficient with that even degree, then your ending behaviors are both going to go down. Okay, they're just going to go down forever and ever and ever. Okay, so they're always going to be the same ending behaviors when your degree is even, and then the sign, S-I-G-N, right, of the leading coefficient is going to tell you which pair of ending behaviors you have, either both up or both down. Now, odd degree polynomial functions demonstrate opposite, different ending behaviors as x approaches positive infinity, as does it when x approaches negative infinity, okay? So when your degree is odd, again, depending on your leading coefficient, you're going to get ending behaviors that are different. So if your leading coefficient is positive, what's going to happen is the right side of your graph, okay, as x approaches positive infinity, your y's are also going to approach positive infinity. The function's just going to keep going up and up and up forever and ever and ever. And when x's approach negative infinity, your y's will also approach negative infinity. So the graph will just go down, down, down forever and ever and ever. But if your degree is odd and your leading coefficient is negative, then the ending behavior is such that the right bound, okay, as x approaches positive infinity, okay, as x keeps getting larger and larger and larger, your y's will actually keep getting smaller and smaller and smaller, so it's going to go down. And the left side of the graph, meaning as x is approach negative infinity, will just go up. The y's will approach positive infinity, okay? So you've got this nice little chart here, and you definitely, it'd be wise for you to commit this to memory, okay? All right, something else that we're going to talk about today is the behavior of the graph with respect to the x-intercepts. So remember, we said that the x-intercepts come from the zeros of the function. Well, we've also talked about in lesson 11, we talked about multiplicity of zeros, like how many times those factors that give you those zeros occur, right? Meaning what is the exponent on the factor? Well, if the multiplicity of the zero is odd, meaning it occurs once, 3 times, 5 times, then what's going to happen is the graph will cross the x-axis at the x-intercept. But when the multiplicity, okay, of the zero is even, okay, so it occurs 2 times, 4 times, 6 times, etc., then the graph will just touch the x-axis at the x-intercept, okay? It'll like bounce off the x-axis, okay? So we're going to put those different ideas together, and we're going to see them in this graph right here. So here's your f of x polynomial function, okay? Now, let's do this zero idea first, okay? Because it's kind of like, how this is ordered, but, and then we'll do the ending behaviors at the end. All right, so this is really, really nice because this is already factored for us. And what we can see is that x minus 1 occurs just one time. X minus 2 occurs just the one time. X plus 3 occurs just the one time. But x plus 4 occurs twice. So I'm going to give that a power of 2. Okay. Now, to find the zeros, we are basically saying, well, when y equals 0, right, what x value will make these factors equal to 0. So it's basically just set each factor equals 0. So one of the zeros here, okay, would come from having x minus 1 equals 0. So x equals 1 would be a 0. And since that occurs just the one time, we would say multiplicity equals 1. Okay. Then we'd take this factor of x minus 2 set to 0. We'd get another x value 2 being a 0. And again, this multiplicity is just 1 because this occurs just the one time. Then we would have x plus 3 equal to 0, and this would give us a 0 value of x equals negative 3. Again, that occurs just 1, so this is multiplicity of 1. And then we've got x plus 4 that we'd set to 0, which would give us an x value of negative 4. Oh, sorry about my oil burning going off. But this has a multiplicity of 2, right? See, because that factor occurred twice, okay? That power on the factor we have is a 2, so that means the multiplicity is 2. Now, what will the behavior of the graph be with respect to the x-axis at each x-intercept? So we would say at 1, 0, 2, 0, and negative 3, 0, okay, the graph will cross the x-axis, okay? Because all those are just multiplicity of 1, which is odd. But at negative 4, 0, right, because we want to state what the x-intercept is, okay, the graph will just touch the x-axis, okay? And again, because that multiplicity is even, so when the multiplicity is even, it'll just touch it, okay? Now, how about the degree of the polynomial and the sign of the leading coefficient? That means if I was to multiply this all out, what would that very first term be? So if I've got an x times an x times an x times an x times another x, right? That would be x to the 5th as my first term. And the next term would be something x to the 4th, something x to the 3rd, etc., right? Well, that highest exponent right there, okay, that's what we call the degree. So this degree is equal to 5. Now, what's important to note about the degree, remember the chart, okay, on the other page, is your degree even or odd, right? That's important to note. So this degree is odd, okay? And then how about the sign of the leading coefficient? Okay, so the leading coefficient, right, Well, what kind of x to the fifth is this, right? What's that number in front of it? Well, that's a positive 1, so we're going to say it's positive. So with those ending behavior, right, with those two pieces of information, what will we get about ending behavior? So again, let's go back to the chart, okay, on the other side. So we have an odd degree with a positive leading coefficient. So right here, this is what we know the ending behaviors are going to look like. So we're going to state this. So as x approaches positive infinity, that means as the x's values just keep getting bigger and bigger and bigger, so as the graph is going to the right, f of x, and remember, f of x is just a fancy way of saying y will approach positive infinity. The y's will just keep getting larger and larger and larger. And as x approaches negative infinity, that just means as the x's go left, right, as the x's keep getting more and more negative, the y's, that's just a fancy way of saying y's, right, will approach negative infinity, meaning the y's will just go lower and lower and lower. Okay, so we're going to write that down. Okay, so as x approaches positive infinity, f of x will approaches positive infinity. Okay, now we can quote unquote call that rise to the right. Okay, is a fancy way of saying it, but this is a layman's way of saying it. And then we would say as x approaches negative infinity, f of x will also approach negative infinity. And then what we can say is fall to the left. Okay, that's just like a easy way of saying it. Now let's look at the graph that's been provided with us and let's see all this going on. Well, let's actually start with the ending behaviors. So when we say rise to the right, meaning as x is approaching positive infinity, f of x will approach positive infinity. That's exactly what we see right there. And then when we say fall to the left, meaning as x approaches negative infinity, f of x will approach negative infinity. There you go. That's like that. Okay? Now, we've got these x-intercepts of 1, 0, which is right there, 2, 0, which is right there. Then we've got -3, 0, and we've got -4, 0, right? Well, what did we say the graph will do at the x-intercepts of 1, 0, 2, 0, -3, 0? Because the multiplicities were odd, we said that the graph will cross, cross, and cross, right? But what did we say the graph will do at the x-intercept of -4, 0? Well, because the multiplicity was even, it'll just touch. So you see it'll just touch. It's like it bounces off of it, right? Okay, it doesn't go through it, it just bounces. Now, let's relate this to what we've already talked about. So you see these x values here at these x-intercepts, right? So this is at the x value of 2, this was at the x value of 1, this was at the x value of -3, this was at the x value of -4. Okay, so what we already said is that this basically divides up the graph into intervals. We've got x's that are greater than 2, right? We've got x's that are between 1 and 2. We've got x's that are between -3 and 1. And we've got x's that are between -3 and -4. And then finally, we've got x's that are less than -4. So this is more intervals than we've done before, but nonetheless. So what we did before is we said, well, let's pick a test value, right? So for x's that are greater than 2, I would pick a test value, let's say, of x equals 3. And then I would find out what is f of 3, right? So I would come here, I'd use the factored form, and I would just go 3 minus 1, 3 minus 2, I'm going to run out of room, 3 plus 3, and 3 plus 4 quantity squared. So I would have 3 minus 1 is 2, 3 minus 2 is 1, 3 plus 3 is 6, 3 plus 4 is 7, and 7 squared is 49. And when I multiply all that together, well, let's see, 49 times 12. Let me see. 49 times 12. Well, there we go, 588. So it really doesn't matter what that value is exactly, but it does matter that it's positive, right? You see that positive? So what would we know about the graph? Okay, we would say that the graph would be above the x-axis, right? Well, look, there you go. There's the graph above the x-axis. And I got that, though, because I found the ending behavior of the graph with respect to the degree and leading coefficient. I knew it was going to rise to the right. I knew that from that x-intercept that was furthest to the right, going to the right forever and ever and ever after that, and so those x's just kept getting more and more positive, but those y's would keep getting more and more positive, and that's exactly what happened, okay? Now, if you were to keep doing this and pick these test values, okay, what would we find about the test value here in between 1 and 2? We would find that the y value would be negative, because you see how the graph is below the x-axis here, okay? in this interval, okay, between -3 and 1, we'd find out that the x value gave us a positive y. No matter what x value we would choose, we'd find out that we'd get a positive y, and then we'd know that the graph is above the x-axis. See how the graph is a whole above the x-axis? And you would know that it would have to turn somewhere down here to cross through this x-intercept, because over here in this interval, the graph would have to be above the x-axis, right? Now, in between -3 and 4, if you pick an x value, you'd get a y value that was negative. So you know that the graph would go below the x-axis. So again, we'd cross through right here, and we'd know that we'd have to dip down. Now, granted, we wouldn't know that the graph doesn't dip down very far, but whatever. And then finally, with an x value less than -4, like -5, we would evaluate our function and we would see that the y's are negative, and that would mean that the graph is below the x-axis. Well, if the graph is going to be below the x-axis for all the x's that are less than -4, then that just means as x keeps getting more and more negative, y's will just keep getting more and more negative, and then it just boop, falls down to the left forever and ever and ever. Okay? So again, I'm hoping that you were able to pick up on these new things that I showed you today, but that you were also able to tie it together with what we've been talking about for the last couple of days. Because I think if you do that, if you put it all together, it makes it really pretty easy to make a graph of a polynomial function. And really tomorrow, so Friday, we're going to just take all these rules and we're going to practice making our own graphs again. Again, we're going to use these new rules, but we'll tie it together with the old rules. And then we're going to break as far as learning new information is concerned. And then early next week, it's just going to be review and quiz. Okay, so that's where we're at with everything with the graphing of polynomial functions. All right, I hope you understood what I taught you from this video. And I've also put an answer key for the homework last night on Google Classroom, and I hope that you have checked those answers as well. And message me with any questions, concerns you have about this stuff. All right, hope everyone's well. Bye.